Welcome! In this lecture, we will explain briefly how the psychrometric carts work, and we will handle the equations relating to absolute and relative humidity. In an earlier lecture, we studied a basic Mollier diagram for humid air and its flipped version, the psychrometric cart. Mollier diagram is also a psychrometric cart, but when people talk about the psychrometric carts, they generally mean the right one. In these diagrams, you could see the saturation line as a function of the absolute humidity, the partial water vapor pressure, and the air temperature. We also drew the lines of relative humidity. Let's look now at the complete Mollier diagram and all its parameters with a focus on the equations used for absolute and relative humidity. A diagram is easy to use, but equations may be needed for more accurate calculations, especially at pressures different from the atmospheric one at sea level. The graphics we used in this course are for the air pressure at sea level. Well, this is how the Mollier diagram for humid air looks like. Let's make first a review of all parameters in this chart. First, we have on the x-axis the absolute humidity. The x-axis is plotted above the diagram, unlike what we did in the slide before. The scale goes from 0 to 20 grams per kilogram dry air. Second, we have the air temperature on the vertical axis, that is the dry bulb temperature, just the common air temperature, going from minus 15 to plus 40 degrees Celsius. Third, there is the dew point temperature that we will define later. Then comes the partial water vapor pressure, PW, that, as you know, is parallel to the absolute humidity. As we have seen earlier, the relative humidity is there. And finally, the density is plotted here, with its value on the vertical axis as well. In other lectures, we will also consider the following parameters: the enthalpy, that you see here. The values of the enthalpy are plotted along the saturation line. There is also something as the wet bulb temperature, and something mysterious called the dH over dx coefficient that goes around the complete diagram. And finally, we see above the sensible heat factor. You may have a preference for using the psychrometric cart instead of the Mollier diagram. So, here it comes again in the psychrometric cart. First, the absolute humidity plotted on the vertical axis right. Then the dry bulb temperature plotted on the horizontal axis below. The partial water vapor pressure is unfortunately not plotted on this diagram. The relative humidity lines are there, while the density can be found here. The enthalpy is shown here and has its own diagonal axis. The wet bulb temperature is there, and the coefficient dH over dx is now to be found on a special graphic here above, while the sensible heat factor is plotted just above. In this lecture, we will focus again on the absolute and relative humidity and the water vapor pressure and derive the equations the Mollier diagram and psychrometric carts are based on. First, some considerations about the absolute humidity X. In the diagrams, it is given in gram per kilogram, but in all equations it must be converted to kilogram per kilogram, which I am indicating with a capital X. Some may find it strange to express X in relation to dry air and not to humid air, as air always contains humidity. If you want to express properties as function of humid air, you can use the formula below. However, as pointed out in the example here, you see that there is not much difference between the kilograms of dry air and the kilograms of humid air, even at the highest water concentration in the diagram, which is 0.02 kilogram per kilogram. We will need later the partial pressure of the water vapor in the air, Pw, so let's look at how to estimate it. The ideal gas law states that the pressure of a gas times the volume it is confined in, let's say the volume in this box, equals the temperature in the box times the gas constant times the number of moles. This law can also be used for mixtures of gas. Humid air is a mixture of dry air and water vapor, which then have to share the same space. The total pressure of the humid air P is, according to the ideal gas law, nRT divided by the volume, where N is the total amount of moles of the mixture. The partial pressure of the water vapor is defined as being the number of moles of water times RT divided by the volume. This is because the dry air and the water vapor cannot be separated from each other. They share the same temperature and the same volume. By dividing the second equation by the first one, we find very easily that the ratio of the water vapor pressure by the total pressure is equal to the number of water moles divided by the total number of moles. As mechanical engineers, we prefer to work with mass rather than with moles. So let's convert this mole ratio to a mass ratio. Of course, the total number of moles is equal to the moles of water vapor plus the moles of dry air. Then I remind you that the mass is the number of moles times the molar mass. The molar mass of water is 18 grams per mole and the one of dry air is 29 grams per mole. We can then rewrite the number of moles N as a function of the mass and the molar mass, see on the right. As we know that N is NW plus NDA, we can now rewrite N as a function of MW and MDA, and finally express the ratio of NW and N using M and the molar masses. And we now come to the last step. If we look at 1 kilogram of dry air, then MDA is 1 and MW is X, the absolute humidity. We can then rewrite the mole ratio, which is also the pressure ratio as seen in former slide, as being X divided by 18 divided by X divided by 18 plus 1 divided by 29. By rearranging this fraction, we get 522x divided by 522x plus 324. If you now remember that x is very small, in general smaller than 0.02, we can then neglect the left term of the denominator, leading to 522x divided by 324, which is 1.61x with capital X, which is 0.00161 small x. So, the partial vapor pressure of water varies linearly with the absolute humidity. You can check in the Mollier diagram that this equation has been used. The advantage of this equation is that you can calculate the partial water vapor pressure for any total pressure P, while in the Mollier diagram it is only drawn for the atmospheric pressure at sea level, which is 101 kilopascal. Let's take as an example a point here in the middle of the diagram with absolute humidity 9.5 gram per kilogram dry air. If we apply the equation from the former slide, the ratio of Pw and P is 0.00161 times 9.5, which is 0.015. The pressure P is the atmospheric one, which is 1 bar, which is 101 kilopascal. Therefore, Pw is 1.54 kilopascal, which is exactly what you see here above in the graphic. In the graphic, it is rounded to 1.5. This brings us to the definition of relative humidity. The relative humidity describes the distance from the saturation line based on partial pressures and at constant temperature. Let's take again the same point in the middle. The temperature in this example is 24 degrees Celsius, crossing the saturation line like this, leading to the saturation pressure PWS of 3. In our example, this leads to a relative humidity of 1.5 divided by 3 is 50%, which is exactly what you see on the card. So, to calculate the relative humidity, you need to know the saturation pressure as a function of the dry bulb temperature. The formula below can be used to calculate PWS, although more complex equations can be used as well. If we take our example at 24 degrees Celsius, the equation leads to a saturated pressure of 2.98, rounded to 3 in the diagram. Finally, I remind you that air humidity is very important for the feeling of comfort. Human beings are more sensitive to heat transfer rate than to temperature, and sweating is a main way to release heat from human body. If the humidity is 100%, air is saturated, the human body cannot release heat, and you will feel much warmer than at lower humidity. If the humidity is 0%, the air is dry, the human body may release a lot of heat by sweating, which will feel much colder than at higher humidities. In this lecture, you got acquainted with the Mollier diagram and the psychrometric card, and know which air parameters can be found on these diagrams. You have learned how to find the absolute and relative humidity on these cards, and you know how to derive the corresponding equations relating partial pressure vapor with absolute humidity and relating relative humidity to partial and saturated vapor pressures of water. This may be useful to make calculations instead of looking at a diagram. Thank you for your attention.